let's consider the knot, and let's draw the free body diagram. Why don't you guys draw the free body diagram for the knot? So please draw the free body diagram. So dot mark for the knot. Think about the forces acting on the knot. We consider that the knot is massless, okay? That means there is no weight. So you can neglect the gravity force on the knot. So we have this force, down tension, and that's T1. Okay, and then our axis is y up, x is that way. So we cannot add these three tensions in ordinary way because they are vectors. So what we need to do is we need to resolve the tensions into x and y components. Okay, so we want to write x components and y components, or you can call x forces or x tensions and y forces or y tensions. So starting with T1, what is the x component of T1? So we need to know the angle first. Okay, so we need to know this angle or this angle to know the component. So what is that angle? So this, if you look at the picture, this chord is at 60 degrees to the ceiling. Okay, so this is 60 degrees. Okay, and this line, this x-axis and the ceiling are parallel. That means if this is 60 degrees, then this would also be 60 degrees. Okay, they are alternate angles. So if you have two parallel lines and you have a line crossing the parallel lines, then this angle would be equal to this angle because they are alternate angles. Okay? So that's 60 degrees. So x component of T1 would be T1. This x component is touching the angle, so it gets cosine. So cosine 60 degrees. And it is in the negative x-axis. So that's along negative x-axis. So you need to put minus sign there. And its y component is T1 sine 60 degrees. Okay. And then for T2, T2 is all along x direction. It doesn't have y direction. So T2 is the y force. And it's positive because it's pointing to the right. Now for T3, T3 is all along y direction. It doesn't have x. Oh, no. Sorry. T2 is all along x direction. I meant to write on this part. Okay. T2 is there. And T3 is along y direction. So negative T3. So we have all the forces and their components. So you add all the forces in x direction and add all the forces in y direction. Okay. So that's negative T1 cosine 60 degrees plus T2. Here T sine 60 degrees negative T3. So this knot is not accelerating up or right or left. So that means its acceleration in x direction is 0. Okay? It's at static equilibrium. So that must be 0 from Newton's second law. So negative T1 cosine 60 degrees plus T2. Same thing here. It's not accelerating up or down. It's at static equilibrium. So this must be 0. So T, this one is 1. T1 sine 60 degrees minus T3. Okay, so we want to solve these two equations to find T2. Okay, so why don't you guys do that? So let's solve these two equations and find T2. can plug in the values. Okay. So T1 is not known, so T1 you can just leave it as it is, cosine 60 degrees, plus T2 is, we don't know T2, and then the other equation is 0. T1 is unknown, and T3 we just found it, that's 98. So we don't know T1, so think about how to eliminate T1 from both equations. So what would you do to eliminate T1? What do you need to do to eliminate T1? So there are a bunch of ways you can do that. Okay, so you can write this as, bring this term to the left, so you can write that as T1 cosine 60 degrees plus is equal to T2, and then you can write this one as T1 sine 60 degrees is equal to 98. Let's make sure I have all the correct signs. So this one is positive, sorry, I didn't write the, so that's that equation. So this is positive. Okay, so that's the equations I have. Now to eliminate T1, divide the two equations term by term. Okay, so divide left side by left side and right side by right side. Then you can cancel T1 and T1. So cosine 60 over sine 60. Okay, that's cotangent 60 is equal to T2 over 98 Newton. So T2 is 98 Newton cotangent 60 degrees, or you can write it in terms of tangent also. So 98 cotangent is 1 over tangent, so tan 60 degrees. That you get if you do the calculation. You guys have calculator? Can you do the calc? 56.58. 56.58, okay. 56.58. I just round it to the least significant digit here. It's 1. So you can write 56.58. And if you use the right significant figure, that would be 60 Newton. Let's look at number 3. So I want you guys to draw the free body diagram for this one. Okay. Question and try to draw a free body diagram. So we have this inclined surface. This is example of dynamic equilibrium. Okay, dynamic equilibrium. So this incline is 30 degrees to the surface. An object is being pulled up. So that's the object, and you're pulling the object with a rope, so that means there is a tension applied to the rope. Okay, that's the first force. Second force is gravity, vertical down. gravity or weight. Weight is always vertically down. And it says there's no friction, so you don't need to worry about friction. And you can also neglect the drag force, okay? Unless the question asks you about the drag force, you can just neglect the drag force. And if a surface, if an object is on surface, then there is also normal force. That's always true. Okay, so you have a normal force. Okay, so these are the three forces you have. So whenever you have an object on an inclined plane, you define the coordinate system such that the x-axis is along the surface and y-axis is perpendicular to that. Okay. So let's write x and y components for these forces, because all we want to do is add x forces and add y forces and equate them to 0, because it's in equilibrium. This is again equilibrium condition. Meaning we can use sum of forces in x to be 0 and sum of forces in y to be 0. That's the concept. So let's write all the x forces and all y forces. So this T is along x direction, so we have tension. And our y-axis is along this normal. So this normal is along y direction. So N. Now this W is part along x direction and part along y direction. Okay, so W is vertically down. It's vertically down. So it has this component and this component. This would be x component of W, and this would be y component of W. So x component, if we consider, we first need to find the angle here. Okay, so using some trigonometry, you can show that this angle and this angle are equal. Okay, this would also be 30 degrees. So you can show this angle to be 30 degrees. I will show this in the lab today or tomorrow, okay? How this angle is 30 degrees. We'll be doing this. But for now, I'll just point out that this angle and this angle would be equal. So this would be 30 degrees. So then, what would be this component? This y component. Would it be W sine theta or cosine theta? I gave you a way to memorize that. So this is the y component of W. Should I write here cosine or sine? Sine. There's a way to memorize that. I already mentioned that a couple of times. So you have this vector, you have this x component, you have this y component. If this is theta, then the side, this side that touches the angle would be cosine theta, okay, f cosine theta. And the side that is away from the angle, this would be f sine theta. Okay, now you can decide whether it gets sine or cosine. Yeah. So this one is W cosine 30 degrees, and this one is W sine 30 degrees, okay? So for weight, we have x component, W sine 30 degrees, and it is pointing to the negative x-axis, okay? So that means we need to write minus sign here. And W cosine theta is pointing down, so we need to put minus W cosine 30 degrees. Okay? Now add all the x forces, T minus W sine 30 degrees, here add all the y forces, n minus w cosine 30 degrees. And then think about what we are finding. So we are finding tension in the rope. Okay? Tension, this equation has the tension. Again, this is equilibrium condition. So this would be 0. And this term has the tension, so we'll be using this one. So T is equal to W sine theta, sine 30 degrees. Okay. You can solve this equation in terms of T. That would be the equation. And T is equal to weight. Weight is mass times G. That's always true. Mass of the object is 70 kilogram. Just right here. Weight is mass times G, sine 30 degrees. 70 kilogram. G is 9.8 and sine 30 degrees. Okay, so if you do that, you get the answer. So it should be about 686 Newton, and if you use the right significant figure, it will be 700 Newton. So number 4 is similar to this one. Why don't you guys try number 4? So start with free body diagram, then define coordinates and see what forces are involved, and then write x and y forces. This is also static equilibrium problem because the slit is at rest. It's not moving. Draw free body diagram first. So you can represent the slit by this dot. So what is keeping the slit from sliding through the inclined surface is the tension. Okay, it's connected to the tension or a rope. So we have tension holding the slit. Okay, so that's the tension. And then it has weight, which is vertically down, always true. And when it's on the surface, it'll always have normal force. And it says it's a frictionless surface, so we don't need to worry about friction. So when you find the weight in the previous problem, you don't need to multiply by sine 30. Weight is always mg, okay? Just mg. But for the tension, you need to multiply by sine 30. Okay? Weight is only. Okay, so the angle of inclination is 30 degrees here. And then you define the coordinate system, x along the surface and y perpendicular to the surface. Okay. And then once you have that, so write all the x and y forces. normal force in the y direction, tension in the x direction, and weight has both x and y components. So let's look at that again. So this is the y axis and this is our x axis. So the weight has part along y direction and part along x direction, and to find those components we need this angle. And again, just like I said before, this would be 30 degrees. We'll show that in the lab. That's 30 degrees. So then if that's 30 degrees, then this component would be W sin 30 degrees. And this component would be W sine 30 degrees. Okay. So x component of W is negative W sine 30 degrees. And y component of W is W cosine 30 degrees. Minus 4 down. Here minus 4 to the left. This is equilibrium state, so sum of all the forces in x need to be 0. W t minus W sine theta is equal to 0. Sum of all the forces along y direction is 0. Okay, and solve these two equations to find normal. So we have normal in this equation, so let's solve this equation. So n is equal to W cosine 30 degrees. So weight is mass times acceleration due to gravity, mg cosine 30 degrees. So you plug the numbers. Mass, the weight is given, so you don't even need to even use this formula. Okay, this is already given. So mg is 77 Newton. Okay, cosine 30 degrees. So that will give you n. Which is 66.68. Okay. We have two significant figures in the question. So that means for the two significant figures, you can write 67 Newton. Number 5 is non-equilibrium problem. It involves some acceleration. So let's look at number 5. Can you make a correction on number 5? So on the last part of that problem, the third line, on the third line, it says 100 Newton, so make that 10 Newton instead of 100. Okay? So correct that to 10 Newton. So it says, shouldn't the tension be mg cosine 240? That's correct. If you consider that angle, you'd get the right one. But we took care of the sine. Okay, we took care of the sine, so that's why you don't need to write 240. You can write 240 if you like, but since we are also considering the sine, so you can consider the angle with respect to the negative x-axis. So what I mean is, if you have a vector like this, you can write this angle as either negative 60 degrees Okay, if you compare with respect to this negative x-axis. Or you can also write this angle as positive 180 minus 60, which is 120 degrees. So whichever way you want, you can write the angle. Okay, so we consider this angle in the previous problem, so we wrote negative sign for that. So we don't need to worry about writing with respect to the positive x-axis. Okay, so let's look at number 5. We have a box that has the weight of 300 Newton sitting on a rough surface. If the man pulls on the rope with a constant force of 20 Newton, what is the acceleration of the box and how far will it move in 2 seconds? Assume the system starts from rest and there is 10 Newton friction force opposing the motion. So consider the box. Okay, represent the box with this dot. Tension would be 343 Newton, not 700 Newton. Let's go back. I think I already. So, which question are you talking about, Cameron? Is that number 3? Tension is on x-axis, so okay, I think what you're saying is, so, okay, I see, okay. So, in this problem, we are considering this surface to be the x-axis, okay? We are not considering this flat surface to be x-axis. This is not x-axis. So whenever we do this kind of problem, that's why we consider the surface to be x-axis. That way it would make our problem a lot easier. 343 is fine, I think, because when you use the actual value of G to be 9.8, I think you may get 343. Maybe I used G is equal to 10, or I did some rounding, so 343 is fine. Yes, so that's the number we are doing. So 70 times 9.8 times sine 30 degrees. Yeah, so that should give you around 350, or even if it is less than 350, that's fine. Okay, because it depends on what kind of calculator you use. Sometimes they round off the numbers. Okay, so let's look at this problem. So draw a free body diagram. We have the push force, which is to the right, and there is friction force to the left. Friction force is less than push force because the box is moving to the right, it's accelerating to the right. Okay, since it's on a surface, so it has normal force, and also there's weight. And weight and normal force should be equal because the box is not moving up or down, it's not accelerating up or down. So these forces need to be equal. Okay, those are the 4 forces we have. And then let's define the coordinate system. So x coordinate is that, and y coordinate is that. So we have x forces and y forces. For x forces, we have push force. We don't need to write the arrow for that, just magnitude. And then friction force is negative because it's to the left. And then normal force, not there, sorry, here, friction force. And on the y direction we have normal force and weight. Weight is negative, okay? So all the forces along x and y. Now, this time it's not equilibrium problem. So that means the sum of forces is not 0. So Fx is equal to F minus F is not 0, but it's using Newton's second law. Sum of force is m times a, okay, along x direction. So m times ax. Sum of forces along y direction is n minus w. Is there acceleration in y direction? Is the box moving up or down? It's at rest, right, along y direction. So it's in static equilibrium for y direction. Okay. So box not accelerating up or down. Whereas here, box is accelerating to the right. Okay. So let's look at this one. So n minus w is equal to 0. That will give us n. N is equal to w is equal to mg. We don't even need to write mg because weight is given. Sometimes the problem gives you weight, sometimes it gives you mass. Okay. If it gives you weight, then you can just write the value. So it's 300 Newton. Okay. So that's not what it is asking. It's asking the acceleration. We want to find this one, okay? So it seems like we don't need to do anything with this one. So here, the force applied to the box is 20 Newton. So 20 Newton. And then the friction is 10 Newton. Mass times acceleration. So mass, what is mass? Mass is not given, but we are given the weight. Weight is 300 Newton. G is 9.8. So that gives us the mass. So 300 over 9.8, that is 30.6 kilogram. Okay, that's the mass. So that is 30.6 kilogram times A. Okay, that's the mass. So 20 minus 10 is 10 is equal to 30.6 times A. So A is 10 over 30.6. That gives us 0.33 meters per second squared. Okay? So that's the acceleration. And it says, how far will it move in 2 seconds? So this is a kinematics problem now. Up to here is the force problem. Now we need to deal with the kinematics. So in kinematics we have 3 equations. One is A is equal to V final minus V initial over T. And then delta x is equal to VIT plus 1/2 AT squared. And then delta x is equal to VF squared minus VI squared over 2A. So think about which one we want to use. Okay? So we want to find the displacement. So that means we need to use either this one or this one. And we don't know the final velocity, so we cannot use that. So that means we need to use this one. Okay? So delta x is equal to VIT plus 1/2 AT squared. And the box starts from rest. Okay? So starts from rest. So VI is 0. So delta x is 1/2 AT squared 1/2. We found the acceleration. And time is given, so time is 2 seconds. Okay, that gives us the displacement of 0.66 meters. That's worksheet 7. Do you guys have any question? So that's all for today. We'll continue our discussion next time, Friday. For the test, I would highly recommend you review all the worksheets. Okay, most of the problems would be similar to worksheet problems. So if you know how to do the worksheet problems, you will be in a very good shape for the test. And for multiple choice questions, I would recommend you to review the quiz questions. So multiple choice questions would be similar to the quiz questions, and the long problems would be similar to the worksheet problems.